Record. Okay, so official start here. We're on air. This is Pkt4 Class 5, Tuesday the 12th of January. Put it up here. Go ahead and set that up. I can see who all's here. I see Brady. Okay. All right. So let's talk about what happened. First off, a couple of announcements. Now on the Facebook group, and you all are the best about going to Facebook. I'm trying to get the in-class kids to go more, but they see me every day. But you guys, so they can always ask questions. But the best place for you to ask questions is Facebook. But first off, I put it's in, and if you don't know, it's ASCII Physics Spring 2021 is the name of the Facebook group. So Shania, you're not a member yet, so you can join in, and if you'll ask to join, I will approve you on the Facebook group, ASCII Physics Spring 2021, because that's where we get a lot of our communication. So like now, the first semester, all the screenshots were going to the Canvas, but ran out of room. So now the screenshots are going to the Facebook group. And the good thing about that is I can put captions on every picture if I want to, if I have time. Also, then what I'm showing you though is, so you have like 11 screenshots there from yesterday with some captions, but then down below, the first comment you're going to find on there will be the link to this wrap-up video we're doing today. There'll be a link there, okay? Just want to point that out. I've now, since your deadline is passed now on turning in 4.1, doesn't mean you can't turn it in today. You'd lose a few points, but that was a 16-point paper that only virtual kids turn in because the others are getting stamps. But here's the key to the front and then the key to the back. And that's posted on the Facebook group in Unit 2, where sheet 4.1 is. So it's the sheet plus it's the key now. I'll do the same thing for 4.2. You're supposed to turn in 4.2. You're supposed to submit that tomorrow. And Bennett pointed out yesterday that the assignments weren't showing up, but now the assignments are in the modules. So I appreciate that, Bennett, for pointing that out. So they're in the modules, your assignments. You can find them there now. You don't have to go to the calendar. Last night on Facebook, Sophia asked a question, and I want to point out something a little embarrassing, but 2 hours. She patiently waited 2 hours for my response, because I don't know. I mean, I don't live on Facebook, so I don't check it all the time. Let's do this. If you do a QFA on Facebook, if I don't answer you, if I don't respond within an hour, then just feel free to text me and say, all you got to do is just text and say, remember my phone number here. Wait, this goes public. I don't want to give this out publicly on YouTube. Anyway, you know my phone number. If not, you can message me and I'll give it to you. But you can text me, just put QFA, QFA, and I'll come to, I'll answer your question. Anyway, I finally started talking to her and answered her a little bit. And then Eric asked a question. I got to him within 43 minutes. Hopefully I can do better than that. But I wasn't just answering his question, but I was giving him some answers. Now, when you submit it tomorrow night, it doesn't have to be right. In fact, every question you answered can be wrong, as long as you put in good effort. So don't be you have the answer at the bottom, so try and get it right, but don't be so concerned. Don't be a perfectionist, is what I'm saying. Perfectionism destroys physics. So don't be a perfectionist. Just do your best you can on that. Give me everything you got, and then move on to the next problem. I will post a key Thursday afternoon to 4.2, and it's a detailed key. So in class, we went around and gave stamps. So far, 14 dogs, including this one. That's 14 stamps, which equates to 28 points. So I'm just going to make it so that when you submit something, you will have the same number of total points as the in-class kids have. So each problem isn't worth the same necessarily for you as it is for them, but I've got to make the gradebook all the total points work out. So that makes the next one worth, I don't know how many points, but it'll add up to be the same points as all the stamps are going out. Now, this is something new this afternoon. I'll post this on Facebook this afternoon. And here are your practice problems. So I don't give you a paper copy of the practice problems. I don't give you PDFs of them. They're just practice problems that go on to the Facebook, and each one has its own post. Now, if you want to print them off, you can, but this is really for your physics notes. All these practice problems are optional. You don't have to do them, just like college. They're optional, but the benefit of doing them is you learn more physics, but the benefit of doing it is that these are the questions that'll be on the test 4A I think for you guys, it's the 29th of January. If you don't work on the practice problems, that test will be a nightmare for you. If you do, the test should not be anything new. I mean, you should have already gone over it all because it comes from the practice problems. Not exactly, but similar, very similar problems. And these can be challenging problems. They're from old tests, from previous years. Sometimes I get them from college level tests. But these are all good physics questions. Sometimes they're easy. I mean, like number 2 is pretty easy. You're just you're sketching in. And so you can choose and pick and choose which ones you work. I'd probably work them all, but maybe do one a night. But this should go in your notebook or just on loose paper, and then you'll staple all that together and you'll turn it in with your notes. So the notes, I think, is worth at least 75 points, maybe 100 points in Pkt4, and a lot of those notes, to tell you the truth, will be practice problems that you've been working on, so that's where you do get credit for it. It will help your notes substantially. If you don't have any, then you'll have really lacking notes. But the main credit will come in where you're getting that 150-point test. You'll be in good shape. So these are the practice problems: practice problem 1, practice problem 2, 3 is all free fall. 4 is free fall. 5 is looks like it's that nut, like the nut falling off the elevator. This is the nut falling off a rocket. Same idea. Supposed to sketch a trio, and then 6 is a more detailed trio. So there's 6 of these. There's 3 sets. There's usually 6 to 7 or so, 5 to 6 to 7 in each set, depending how long each problem is. So we're talking about 18 to 15, let's say 15 to 20 problems when you add them all up. And that's how we'll do the first test on a packet. The second test will come a couple weeks later, and that'll be from the take-home. We'll do an old take-home. So the first test is 150 points. These are optional. The second test is the take-home test that goes with it, which is another 100 points or so. And then a 300-point test. That's test 4B. That's going to be in February. Okay, so that starts today this afternoon. As soon as we get done here, I'll start to put those on Facebook. Okay. Also, yesterday we talked about the 4 fundamental forces, and we talked about the carriers of those forces. And one of the carriers was photons between electrons, or between protons and electrons, or electrons. So like 2 electrons repel each other. And I was born in 1959. That's about the time that Feynman diagrams came out, that Richard Feynman developed this way of visualizing quantum physics. And so you learn in chemistry that like charges repel and opposite charges attract. That's one of those fundamental chemistry rules, but they probably did not explain to you why that is. And the reason is explained through a Feynman diagram. We talked about this yesterday. Photons being shot between electrons. One electron being excited, and an excited electron, in class I was showing them pendulums. and talk about things being excited, things being in ground state. Either an electron's in ground state, which is the slowest possible energy level, or it's excited. And so when an excited electron gives up one of its photons, gives up a photon, it shoots it out into another electron. The electron picks it up. So here comes this electron along, but it's excited. It's in a higher energy state. You guys learned the Bohr model in chemistry, if you took chemistry, of 2 electrons in the first level, 8 in the next, 18 in the third. There's that n squared rule, 2n squared rule. But that's the Bohr model. All of those electrons are ground state electrons. When you shine a light on it, or you give some type or an X-ray or a radio, even a radio wave on small changes, that gives the electron energy, and the electron does a quantum leap out to the next level, or maybe it jumps out 2 or 3 levels. Okay, those electrons are considered excited. An electron cannot continue to be excited. It cannot hang on to that energy, and it throws it up in the form of photons. So here's an electron, an excited electron coming along, throws up a photon. It cannot hang on to that. And the photons this is all in the form of waves. Tomorrow we'll start talking about simple harmonic motion. We'll start talking about waves, because really most of physics, once you get to the wave equation, physics is all waves after that. So anyway, so the electron coming along here, excited, it gives up that photon, and then there's a recoil involved. Like as if you were shooting a bullet out of a gun. There's a recoil involved. That electron bounces back. This electron that's in its ground state, a low energy state electron, absorbs that photon, gains energy, and then bounces off this way. So this is the reason, at least from a Feynman diagram point of view, it's still somewhat simplified, but it's the reason why electrons repel. Is they're pew 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 pew. They're shooting photons at each other. And that brought up the question of this gluons, like gluons in a nucleus. Those are attracting. That's not photons. It's not the same thing. But gluons also have gluons are like between quarks. They're like, in fact, they've been likened to springs. The further apart they go, the more they attract. It's weird. But that's what holds things together. So gluons are kind of like photons. But then we have this mythical particle that's called a graviton, and we haven't discovered it yet. We talked about yesterday, you get a Nobel Prize if you find it. But gravitons somehow hold objects of mass together. And what's the nature of a graviton? Are they shooting particles? But no. Are they like harpoons where they are? So between any two masses, there are, we theorize, that between this bottle and this pin, there are gravitons, because it has mass, holding them together. Now it doesn't really play a big role until I drop my pin. Well, now the Earth, now you have a tremendous amount of mass, and the Earth's gravitons somehow pull the pin from this theory, okay, that pulls the pin down to Earth, or holds the moon. So is the moon and the Earth shooting gravitons? It gets a little crazy, right? Yeah, Einstein would say a lot of that's kind of nonsense, because it's basically just curvature of space-time. So there's something called the gut. The gut. And then I promise I'll get off this. I mean, part of my standards here is I'm supposed to talk a little bit about modern physics, to a high school student. You ought to have some inklings of the way things work, more than just classical physics. So the gut is called the grand unified theory, and that's what scientists are still trying to figure out. Einstein, on his deathbed, had his pen in his hand and was still writing equations. They had to pull the pen out of his hand, because to his death, he's still thinking and trying to understand the universe. So from the time he was in high school till the time, even when he was a little boy, he still tried to understand light. So from the time he was like 4 or 5 years old to the time he died, he was trying to understand. That's a life well lived. But that's called the gut. So somehow gravitons, they're trying to put all the forces together. They can't seem to get gravity in there. They're trying to get all the forces together in a grand unified theory. Einstein couldn't do it. They still haven't been able to do it. Okay, he died in the, I believe, the 50s. He was at Princeton, which one of our students is now going to go to Princeton next year. She'll be the same place that Einstein was. Okay, so that's sort of yesterday's repeated. So the last thing is on this, electron goes from excited state, shoots out its photon, goes back to its ground state. Another electron that was in the ground state absorbs that photon and becomes quote excited. It will then pass that on to another electron. And this is happening right now all over the place, all over the front of your face. It's happening inside your body. It's not some weird physics lab somewhere in Cambridge. This is happening right now all over. Here's my evidence. Color. Red, the color red is when an electron throws up a photon that has a wavelength of 600 nanometers. Our eyes interpret that energy as red. If it throws up a photon that has a wavelength of 450 nanometers, we see that as blue. So my evidence is the colors around me. I mean, this pill, this vitamin C bottle, this red right now, when you're seeing that red, you're seeing these electrons giving up photons, okay, dropping down into lower energy states. So it happens billions of times a second. Physics, that's the cool thing about physics, is that, yeah, we're doing kind of, classical foundational physics in here. Every once in a while, it's kind of fun to talk about, modern day. But physics will never disappoint you. It'll never bore you. You might understand it. You might need to catch up with your math, but I've been studying for 40 years, and it gets more interesting the longer you study it. You can't say that about a lot of subjects. Some subjects just get stale after a while. Economics, okay, that can be exciting, I suppose. But things like that, just, I don't know, biology stays cool, chemistry stays cool, science stays cool. But physics is the foundation. The reason I love chemistry is because of the physics of it. Homework. I pulled this chestnut up from a couple of years ago. This was, and I'm just going to say a quick word about it. This was the nut that fell off the elevator. And I think a couple of years ago, a kid asked, well, how do you know, like in that quarter second after it falls? This was your homework. This was number 3. We did this, I think maybe 3 or 6. I don't know. One of these problems we did on 4.2. And, or was this 4.1? Anyway, it was one of those. And the question was it going up or was it going down? And so the kid really wanted to know. So we blew it all up and looked at it. We found out that a quarter second after it falls off, it's still going up. This brought up the whole idea of inertia and momentum, okay? All came out of that little problem. But you notice that nut falls off the elevator. It does go up a little bit. That's this green triangle. But it falls down a bunch. It spends a lot of time going down and a little bit of time going up. And so the velocity looks like that, a very skewed bow tie. The position versus time, of course, is a negative parabola. One of those types, remember, reaches apex and falls down below. And this is your homework that you're currently working on. And I'll post this key too. So this you could go back. This is number 4 on sheet 4.2, and feel free to go back and look at this. This doesn't necessarily answer all the questions, but it is a negative trio that goes with. This is the case where you drop the bottle off that hot air balloon, if you're familiar with the homework, and the bottle continued to rise, right? Initially, it's rising at 50 meters a second. And then, of course, gravity starts to pull it back. And so that's what's happening here. So it spends a little bit of time going up and a lot more time going down. It ends up falling at about 150 meters a second before it hits the ground, assuming no air drag. And then that gives you how far it fell, a little over a kilometer. Okay, from where it was let go. Okay, let's keep moving. I can't show you this yet. I showed it to the class because they're now officially done with 4.2. You still have till tomorrow night to submit it. So I don't want to show you the key. I'll post this key Thursday afternoon, but I want you to first try these on your own, not just copy off the key. Okay. Not that you would. All right. So here we go. Today's physics. We are going to look at developing the 2 green equations. So in your packet, get out 4.3. Here's a color version of it, but get out 4.3. You should have a packet of papers. Shania, if you don't have it, Shania, you probably ought to email me or text me or something, and so I can get you kind of set up with the class and find out more about you. Okay. All I know about you is you're very quiet. Okay, so this is the front, and on this part, this is where we collect some data. This is for Thursday. We would do it today outside, but it was a little cold. I'm thinking Thursday will be a little warmer in the morning. I'm mostly concerned with first hour. So we went in and talked about it today, and we're going to actually go out there and do it Thursday. But let's go ahead and derive. Skip the front for now. Let's go to the back. We're going to derive on the back. Hold on. Okay. On the back, we're going to do these 2 things. We're going to do the launch equation derivations. All right. There's 2 greens. The green equations are a subset of blue, and they're called the launch equations. Okay. So here's the setup for Thursday outside. And I'll post the screenshot. The basic question we're trying to answer is, what is the launch velocity of that rocket? Okay. Now in rocketry, which you all, if you're juniors and sophomores, you're free to join our rocketry next year if I can talk Bab into doing it another year. But we launch these G motor rockets, pretty big rockets. This little rocket we're launching on the West Lawn Thursday is just an air rocket. It's no big deal. Normally it's Estes, but I'm out of Estes, so just a little air rocket. It makes the point. But we're trying to figure out how fast that rocket comes off the launch pad. Okay. Now the ones we launch in May for rocketry, those come off at supersonically, so they come off at like Mach 1.5. But this one won't come off that fast, but it'll come off pretty fast. So we're going to try and determine the launch velocity 3 ways. One, we'll have some people with slow-mo cameras that can slow-mo it and see if we can get a couple of frames in of while it's moving. And then one group will do it through tau. That'll be this group right here that does it through apex time. And one group will do it through angles. Okay, so in the next time we have remaining here, let's talk about those different approaches. All right, and these are called the green equations. So let's start off with the easy one, and that's the first green equation derivation. All right, so in a green equation, you're trying to find that launch velocity using just whatever you have. So let's say all you have is a timer, and I want to know what V launch is. So if all I know is the time, I know nothing about delta Y, I can't use the second or the third blue. I have to use the first, right? So in the first equation, so for the first green, we'll start with the first blue. So this is a derivation. We're going to derive the first green equation. Okay, so we start with the first blue. So we start with V final equals V naught minus GT in general, GT. Okay. Now what the timers are going to do is they're going to start their watch or stopwatch when the rocket is launched. They're going to stop their stopwatch when the rocket comes back and hits the ground. Okay. So, yeah, so they're going to measure tau. Okay. So what they're going to look at is they're measuring the total time of flight, but we're trying to figure out the V launch. So what we do there is for green, we instead of saying V final, we just go halfway up. We say V apex. So V apex is equal to 0, right? Because initial velocity at the apex, and we learned this, anything at the apex, the y velocity is 0, equals V launch, or V sub L, that lowercase cursive L stands for launch. V sub launch minus G, and what is our particular time? Somebody jump in there. What's the time at apex? If the people on the ground are measuring tau, what's the time at the apex?
Half tau.
Half tau. So thank you. So tau over 2, half tau. Okay, great. So then look how easy it is. The V launch then is simply gravity times half tau. I mean, that is pretty easy derivation, easy to work with. Problem, here's the problem. 3 big problems. Here's why it doesn't work so well. Problems. First problem is I can't give you a countdown. No countdown. Because what I'm going to have on Thursday is I'll have my air compressor there. And so we'll just pop. Well, I don't know when the daggone thing is going to pop. I mean, there's a lid in there and it reaches enough pressure, it finally pops, which shoots the rocket up. It goes up fairly high. So there's no countdown. In other words, I can't give a 3, 2, 1. Well, the problem there is students, even though you're much more reactive than I am, you have a plus or minus, even the best students have a plus or minus 0.15 error, built-in error, just in your eyes see that it launches, and then your hands finally, your finger finally hits the, and by the way, that's doubled times 2 because you don't know when it's going to launch. And so finally you hit the start button when you see it launch it. And then it comes back down and it's not like it's black and white, like, okay, I think it hit the ground, and you hit stop. So there's the error. The other error is hard to know, hard to anticipate hitting ground, right? It doesn't give a bell or whistle. You say, I think it hit the ground. Okay. Sometimes you don't see it very well. So those are all errors in this seemingly great way to determine launch velocity. Okay, so we will try that method. That's one method. The other method we're going to do is using angle. So I don't have it with me, but at school I'll show you there's a gun. We're going to use an altitude gun. Okay, so this requires, so this is an altitude gun, and the altitude gun, you hold it, and there's a little trigger you hold on the altitude gun, and that allows this little thing to swing back and forth. And then you hold it up, and then you let it go when you reach the apex, and that gives you can look off there and see the angle that you're at. So that's kind of cool. So We have 4 of them. We had 5, one busted. But we have 4, and so we'll have 4 people over there doing the angle. So let's draw that out. This is line of sight. LOS. Line of sight. So the line of sight will be, and those 4 of these have to agree, and then we'll have some angle theta, and they'll come back to us and tell us what the theta was. This will measure, they'll be standing exactly 100 feet away from the launch pad. And we can get 3 siggies out of the 100 feet. So, because we can go exactly, we can be within the nearest foot easily. So that won't be hard. So we'll have 3 sigs there. The timing on this this other way of doing it, the best you're going to get is 2 sigs. So that is a 2 sig situation, which is not terrible. 2 sigs. And pretty bad because 0.15 error plus or minus is really turns out to be plus or minus 0.30 seconds error on that, which is bad. Okay, so they're sitting over here looking at the line of sight, and from there, from the launchers, they're supposed to come up with what is V launch, just knowing that and knowing the 100 feet. So if you don't know time, which blue equation do we use?
The third.
Right. So this is the derivation. This is the one you left in our test. This is the derivation of second green. We start with the third blue. So we have V final y squared equals V naught y squared minus 2g delta y. Okay. So we're looking at it from a launch point of view, from an apex point of view. And so if I just go the apex, let's go green. If I say V final apex squared, well, that's just 0. All right. 0 squared is 0. 0, I don't know, that's stupid to put squared there. I'm going to do it. 0 equals, well, now my V naught is my V launch squared minus 2g. And this is not just any old delta y. This is the height. So we put 2gh. Okay. So this is h here. Kill that. This is h. All right. Well, wait a minute though. I get it. Let's go ahead and solve for V launch then. V launch then is simply the square root of 2gh. But the problem is, I don't know what h is. Anybody going to help me out here? How can I find h?
The second blue? Well, no, never mind.
Yeah, well, we still got too many unknowns. Second blue requires time. How can I find h with this information and this information? Think back to trig.
Tangent.
Right. So yes. So I think both of you said the same thing. So SOHCAHTOA, right? Sine is opposite of hypotenuse, cosine is adjacent. The problem is hypotenuse is that line of sight. We don't know how long that is, but we do know the adjacent side. We do know that, and we're trying to find the opposite side, and we know theta. So in this case, h. Okay, let's run through it here. So a little trig. So tangent of theta is equal to opposite, which is h, over adjacent, which is delta x. So therefore, h is equal to delta x times tan theta. Okay. So now we write the full second green equation. And these are now hanging from the room. V launch from the ceiling. V launch equals the square root of 2g delta x tan theta. Now that's a derivation you're going to have to know for test 4A. Boom, second green. Remember, the greens are a subset of the blue, which are a subset of the orange. Okay, so on Thursday, we're going to use this equation along with these two equations. Now, whoa. Hold it. Now let's talk about sig figs. Well, the G's got as many sig figs as you want. That's got 3 siggies. 3 sigs. The delta X, we can measure 100.0, we can measure 100 point feet, right? We can get that to the nearest foot. That's 3 sigs. That's why I want to go 100 and not 50. You want that extra sig. And then theta, that's the problem. We probably only have 2 sigs there. But I contend that 2 sigs there is probably plus or minus a couple of degrees. Let's say even plus or minus like 4 degrees is still better than plus or minus 0.3 seconds. So I still think that this will give me a better data than the tau. And maybe the slow motion camera will give us good data. I don't know. It's hard to get it in the frame. We'll have to stand back, those doing slow motion camera. And that's why I say, if you want to come Thursday and take part in this, physics is a lot better when you're actually doing it. Me sitting there telling you about it, it just make your eyes glaze over. But if you do it, physics needs to be active. So, okay, so that's the main thing for today. Now, any questions, let's stop here. We're gonna table this until Thursday, and then I'll put a little video of it, and I'll show you. Tomorrow we're getting into oscillations. You kind of do all this. Physics is hard to teach, A to B to C to D, because everything, we talked about oscillations with photons, but we need to talk about oscillations now because it's going to come up and up and up in the rest of the year, oscillations. Yeah, so anyway, so tomorrow we'll start talking about little oscillations. But any questions on all this stuff? And this should go, okay, here's where I put it. I put it like that. That's sort of, I actually, tell you the truth, I think this looks better. This right here that we did, I'll put this screenshot up there, but you need to put something in here so you get credit for it when you go up and turn the packet in. Okay, well, we'll try and finish a little early today, but in the time we have left, let's look at 4.4. That's the homework tonight. And the 4.4 has got no new equations. But the thing about 4.4 is it's symbols only. So, we say that to work a physics problem, you do CL-DPA. Well, there's no C, there's no circle, there's no label, there is a drawing, there's an equation, there's an isolation, but there's no numbers, there's no units, there's no worry of units, there's no plug in, there's no A. So of the CL-DPA, we only hear on these symbols, we only worry about drawing, equation, and isolation, okay? Drawing, equation, isolation. When you take the AP Physics exam, at least when I was teaching it, you don't get a calculator. There's 35 questions you got to do, and they're multiple choice and all, but you don't get a calculator. So it's all just symbols. And if there are numbers, they're simple, like 4 divided by 2. I mean, it's just simple stuff that you don't need a calculator for. I don't know, that may have changed now. I don't know if you get a calculator or not, but back in the day, you didn't. I haven't taught AP in 5 or 6 years. Probably 7 or 8 years, actually. Okay, so that's Mr. Pentecost now. Let's look at this, and I'll work one as an example, and then the homework for a half a dog each. Now for you, I think this will probably be due for you, but it won't be this week. It'll be next week. You'll just submit it. Yeah, I guess. I gotta pick a paper a week for you guys, just so you're getting your dog points, your stamp points, just to keep you up with the in-class kids. All right, so let's work number 1. I'll show you what I mean, and then you can do 2 and 3. These are pretty quick because there's no calculator necessary. They work pretty fast once you get the hang of it. So let's try number 1. It says this is the last thing we'll do. It says find the initial velocity of a bullet at a certain distance from the end of a gun barrel. So the bullet is inside the barrel. That's not totally, it's not a well-written question, I must admit. But the bullet is inside the barrel. It's somewhere, it says the initial velocity inside a barrel. So here we have a bullet and it's going along inside a barrel. And then it says at a certain distance from the end of a gun. So this is our delta X. You got to read these carefully. They don't take a long time, but you really got to read the question over and over. It makes you really understand reading the question. A certain distance, that means I know the distance from the end of a gun barrel undergoing an average acceleration. So therefore I know the acceleration. If it leaves the barrel at a particular velocity, so the velocity leaving the same bullet now leaving the barrel, I know what V final is. So yes, I know delta X. Yes, I know acceleration. Yes, I know V final. I'm saying my question is, what is V naught? Now, to solve these, you're either going to use orange, the 3 orange equations, the 3 blue equations, the 2 green equations, or black. It could be circular motion, black equations. So you have like 11 equations to choose from. That's the hardest part. Pick the equation you're going to use. So what do you think? Look this over. Which equation should we use to solve this?
Third orange.
Third orange, right? We're not getting, thank you. Whoever said that, give yourself a point, a zoom point. Now, we're not, you'll write that. You'll write all your zoom points on the cover sheet for Pkt4. Since we don't know time, we had to use third orange. So you're correct. So here we go. First, you write the equation down. So we have V final squared equals V naught squared plus 2a sub x, or 2a delta x. Okay. Trying to solve for V final, or V naught, I mean. So V naught then squared then is V final squared minus 2a delta x. And therefore V naught is the square root of V final squared minus 2a delta x. Box that in and you're done. No needing a calculator, no unit analysis, none of that stuff. Okay, so symbol problems are really good to practice because it forces you, because a lot of students, they do physics, they just want to start throwing numbers at a problem. Give me an equation to plug into. F equals MI. Oh, plugging M in. You're not really doing physics. You're a monkey plugging numbers into a formula. You don't understand what you're doing. This is forcing you to understand the symbols, okay? Not just plug numbers into a prescribed formula. That's called cookie cutter physics. And that's not good. I'm not saying I don't do it sometimes, but you know. All right, so you go and do the same thing with 2 and 3 and then call that good. I want you to spend most of your time at night working on practice problems because that's your most bang for your buck. No, you don't get any bang for them except for the credit you're going to get on your notes. But the big payoff comes January 29th when you take the test. Okay? Any questions? Let me stop the sharing. Hey, we're going to finish early today. A little bit, 5 minutes. Any questions? Shania, go to the Canvas. I guess that's how you got here, right? You must have saw that. Go to the Facebook group and join. And then you can message me on Facebook, or you can just You just message me on Facebook, and then I'll give you my phone number when you do that. I don't want to give my phone number out on YouTube, on public YouTube. Okay. Anybody else got a question? Feel free. Tipton, Eric, give me some. Brady, give me an icon for you guys. Oh, I'm gonna do a quick screenshot. Don't leave. Don't leave. Don't leave. Quick screenshot here, and I'll use that for roll. I can kind of see who's all here, but okay. All right, everybody. I'll see you guys Wednesday. Have a good Tuesday. I'll see you tonight on Facebook. I will try and respond faster than last time. Bye-bye.